Hello, everybody. Welcome again to another live stream. I'm Stephen, owner of Learn CMM and victoryprogramming.com. I'm going to go ahead and share my screen again. And we can dive in right away. We're going to play with this part that I'm showing here. This. Actually, my son modeled this part. He's pretty proficient at SolidWorks. So this has some interesting angled holes in it, and we have an RDS sensor, which we can use to get those half circles or half cylinders at a specific angle. And again, if you have any specific questions, even if they're not related to this program, feel free to chat and type your questions in the chat, and we'll see if we can answer those in our half hour. So let's get started. So this is just a blank program. We're going to build it from scratch. So I need to start with my alignment. I'm just going to turn off this simulation for now. Now, every part is unique, and when you're setting up your alignment, you have to think about what is the best way to locate that part, and ideally the simplest way of finding it manually when you do the manual alignment. So first thing I'm going to do is I'll plan on setting up this part, if I had it physically, on a V block on this cylinder facing the way it is oriented right now. And then I'm going to create a plane right on the top. That's going to be my leveling plane, or the rotation in space. So down here we go extract features and plane. I'm also going to create a circle, and I'll do it on the outside diameter. And we also do need something for the rotation, because we have these half cylinders in here. This is a little bit tricky because you can't get those from a straight down probe. So what I'm going to do is I'll add in a circle that's angled right here. And we're going to have to rotate the probe to get that angled circle. You know what? For the base alignment, I think we're going to need to do a cylinder off of there, and then we'll intersect it to create a point on the plane. The reason why I'm not going to do just a circle is because if the operator manually takes that lower or higher, that could throw off the angular alignment quite a bit. So this is a little bit of a unique part, kind of some advanced moves we're doing here. But let's go ahead and create that intersection point. So from the cylinder to the plane. So we'll go construction, intersection, and then feature 1 and 2. Since I already extracted these from the model, I can use select already extracted features and then just click on the model. And it puts them in there. So here we have a little blue X, and that's our intersection point. Now you'll notice sometimes if your settings are turned on this way, the geometry that gets extracted will turn this like this light bluish purple color. And that's this setting right here under geometry, show all CAD elements with geometry reference. And sometimes it's helpful, sometimes it's not. It helps you know what features you actually extracted from the model. Otherwise, you can have it off. Okay, so this plane, I do need to add in some points or a scan, because you'll notice this white indicator means there's no strategy. So I go to strategy, and I can put in some individual points, or I can put in a circle path on that plane. So I'm going to just put it kind of halfway in between surfaces. And I always tell people when you're scanning something with a probe going straight down on a plane, you want that speed to be less than you would use on a cylinder, because imagine if you take a pencil with the eraser on the paper and you press and slide it. It's not going to slide very smoothly. It's going to kind of bounce on that paper. And that's kind of similar to what's happening with the probe on the surface. There's a little bit of micro vibrations happening because of that perpendicular scan. So all that to say, anytime you're perpendicular scanning on a plane, you would go a little bit slower than you would on a cylinder. And we'll change our step width or point spacing so we can get a good amount of points. And that's good. The circle, you can set the strategy on that. We can go a little faster. And then the cylinder, I'm going to do just 2 circle sections. And a little tip on this. So anytime you're doing a cylinder, you can do either individual circle paths, or you can do a single circle path line item with multiple paths. So this makes it easier because then you can do a bunch at a time and manage the speed and the spacing and everything within one window. Otherwise, like if we did this way, we'd have 2 in one window. Otherwise, we'd have to go and do a separate circle path for each one. And then if you decide to change any settings, you have to go in each one and fix it. So if you know ahead of time that both of them are going to be the same angle range, same point spacing, just do one of them and then tell it how many paths. So then the start and target height are relative to where the cylinder local origin is, or the base of that cylinder. So let's say we're going to start up at 15 millimeters, go up to 35 or so. You can drag on the model, so that's easier sometimes. So I'm going right below the chamfer here, and then we want our angle range to be less than 180, but I'm just roughing it in right now. You can also drag this little X, and you can drag the arrowhead. So there we go. And just in case this edge is not exactly there, we don't want the probe to fall off. So you're always thinking about, what if the part is not perfect, or what if it's not aligned perfectly? You got to accommodate for that. So notice the CAD view is a little bit choppy, and that's often common. Even if you have good graphics, sometimes you have to go and force it. Go to CAD settings, view, display quality, and then very high. And if it's still giving you problems, you can turn off the surfaces. That just makes it easier. Okay. But you notice up here it looks good, but down here it does not. So this is a situation where we do need to have 2 separate circle paths with different angle ranges. So this one is going to be one section, and then we're going to copy that and put the other one down at 15. And if you have one section, the start and target height All that matters is just the start height because you're not having multiples. So, oops. Sometimes if you accidentally click here, it'll mess it up. So you can click reset, or reset here will reset the entire thing. So drag this one up, and this one we're going to go at 5. All right, I'm going to pause for a couple of the comments. One is explain the 3-2-1 rule. Yes, we can definitely do that. We'll jump over to a simpler model. How many types of alignments are there? We can do an overview of alignments. And those were from Ravi. And Jeff is saying, I'm waiting for Zeiss to add the very, very high display quality. Yeah, that's funny. Some of the models I work with have small enough features to need it. So yeah, Calypso is kind of notorious for kind of glitchy graphics stuff. So you have to be patient with that. Inspector T, sometimes is it okay to measure a cylinder as a circle for position? Typically the rule of thumb for that is if the depth of that cylinder or how long that cylinder is the same as the diameter or less, then it's fine to measure it as a circle. If it's longer, it's better to measure it as a cylinder because then you're not only checking the location, but also whether it's tilted. So especially for something like this, if we only check it as a circle is a two-dimensional feature, and that wouldn't allow us to evaluate the angle. And then another guy, another person, Apaso, explained the best fit alignment. So after this, we'll go over some of those questions. Okay, so once we have our path set up here and it's not going to fall off, you want to get as much of that as you can, just so you're having a reliable measurement. But then we can go ahead and throw in our base alignment. And I'm going to create a new base alignment. This window here was recently updated. I believe it was 2024 or 23. So it might throw you off a little bit if you're used to the older versions. But this little icon is for a new alignment. And again, I can use select already extracted features. Got the plane there. Cylinder or circle for X, Y. And then our rotation, I can't pick off the model because it's a constructed feature. So I'll go in here, intersection 1. And I want it to rotate that towards the Y positive. So we're oriented this way. Nice. Okay. Put in the clearance. All right. So with this, I just, with the time we have, I want to cover how would I add a probe angle to get that cylinder using the RDS. So if we go to CMM tab, Stylus System, I'm also going to turn on the simulation so we can visualize what's going on here. So we have a 5mm probe. You'll notice if you ever use this simulation, you'll notice sometimes if you set up your alignment on the part, the probe will not be oriented to the part perfectly. But once you run the base alignment, it fixes itself. So I'm going to do that really quick here. With the simulation on, and just run through this. So it will fix itself. And then we'll grab this cylinder. Notice it's not at the correct angle yet, but I'm just doing this so that the simulation will be realigned to the base alignment. So I'm having it run through that. Once this is done, then we can set up that angle to match the same angle as the cylinder. Okay, so once I close the simulation, reopen it, and then if I go define points to click on the model, now my probe is lined up. Okay, so now we want to create a new probe angle. So go to the CMM tab, stylus system, and most people, when they use the RDS, they're qualifying each angle as a separate stylus. There's another mode called CAA, which is where you qualify 12 specific angles, and then you can use any possible angle, and you have one stylus name. But I'm going to do the first method. So we're going to add a new tip. But before I add a new tip, I have to decide what is the angle I need. Now I could go extract features on this cylinder and try to use these angles, but those are not going to work. And the reason for that is because those angles are referencing the X and Z axis and the Y and Z axis. But we need angles that represent A and B. So if you're not familiar with RDS, the A angle is going around the head. So if we rotate, let's say 20, that's A20, A40, and so on. So it's going clockwise around this part. So A90 would be like that. B angles are around the wrist. So B20, B40, and it's going to the right is positive, going to the left is negative. But we need to figure out what is that angle on the cylinder. So there's a nice feature in here. If you have a feature selected and you have this window open, and I got to this by this rotate probe button, you can click this one right here, which says rotate the axes to the feature selected in Calypso. So there it is, A minus 10, B minus 20. Now it might not be exactly that angle, but it has to round it off to the nearest 2.5 degrees. Then if you're on a physical CMM, you would click this button to rotate the axes on the machine, because this is just a preview. This would physically rotate the head. Okay, and then another thing you can do, if you have this angle active, is you would click this third button. No, wait a minute. See, in the older version, they changed all the icons, but there is it's not that one. See, there was a button that where you could apply this angle to that feature. That's why I like the older version sometimes. Oh, that's for the CAA. Never mind. We will get into that maybe another time. So anyway, so once you have that angle, just click yes. We can go to our stylus system and we can add a new tip. We'll call it, what was that angle again? A minus 10 or something. Let's find it. Let's go back here. Click our button again. Okay, A minus 10, B minus 20. Go to our CMM tab, stylus system, and new tip, A minus 10, B minus 20. I would call this number 6 because it's not one of the regular directions. And then Sometimes it'll switch back to make sure the correct angle is active. And then we go qualify. And once you qualify that, then you can use that tip for this cylinder. Now this is definitely a good part we can use for next time. We can do more. There's a lot of cool stuff we can do for constructions. We can talk more about this controlling the probe travel. But I'm going to jump over to your other questions. We're going to switch over to more foundational topic. What is the 3-2-1 rule? Okay. So on a part like this, where you have primarily level surfaces, you have planes that you could use to locate the part, the 3-2-1 rule is the minimum number of points you need to constrain the part. So according to the CMM, the part is initially it's just floating in space. The machine doesn't know where the part is. So in order to line that up, we would have to have something for the leveling. So we could do 3 points to create a plane that would level the part, kind of like a 3-leg stool is going to be leveled. So you need at least 3 points for the leveling the part. Then 2 points in another direction to establish the rotation. So this would create a line for that twisting of the part. And then 1 more point for the origin in the X. And I did make a video on this topic about understanding basic alignments. And there's like an animation, and you can see how those 3 datums will constrain the part in space. So you can check that out on my channel. Another question. How many types of alignments are there? So every alignment can be slightly different depending on what features you're using. You might have a plane for leveling the part with a line for rotating it. You might have a plane rotating to a circle, like if you had alignment off of this plane and one of these circles with a bore center. So those would be from your regular alignments. But there's other types of special alignments that you might use under resources, utilities. There's a 3D best fit, RPS, P6, geometry best fit, alignment from curves. And all these have a specific use cases. So a 3D best fit, that is typically used if you have a whole bunch of random points on the part. And you can also use even spheres or circles, anything that would resolve to a point. And it takes all the nominal points where they should be, compares it to the actual points, and then fits it. So if you have a part that's really weird and there's nothing flat on it, you could use a 3D best fit. RPS and P6 are similar, and those are kind of like an alternative to a 3-2-1 alignment. If you have maybe a car body part and it's kind of flat, but it's curved, so you could have 3 points for kind of a plane and 2 points for kind of a line, and then another point for an origin. And those would be all called out from datum targets. And then a geometry best fit is if you have like traditional geometry, like a plane, cylinder, and so on, and you can best fit those together. So it's using them all together to fit the alignment. And then alignment from curves, again, that's similar to a 3D best fit. You're taking all the variation and reducing it down to the least variation. All right. And yeah, the alignments is a deep topic. There's so much to learn, so much to cover about alignments. So, and I know that's often a pain point with people, so we can definitely go over that again in more detail next time. Any other questions? So we have How would the model, without a model, how do you make a 2D curve? So that is possible. You can make curves with no model, and that's called digitizing. It's a little bit of a multi-step process, but in a nutshell, you're going to create a blank curve. You're going to come near the model, activate the setting for digitizing, and then you're going to probe the very first start point, and the probe is going to scan and find that whole surface all the way around. After that happens, then you have to massage the data a little bit to make it cleaner, but it has been done. I've done that a few times. All right, let's see. Other questions. Daniel Lopez said Zeiss just came out with the latest service pack for 24. I did see that come in. I haven't had a chance to install it, but I always try to install the latest service pack as soon as I can. Just it resolves any buggy things you might see. And then one other question. Can you explain and give an example of a kink point and a step point? All right. So a kink point, a step point, those are similar but not exactly the same. So let's start with a step point. So it's under construction, step point. This is handy if you have two cylinders and the diameters are very close and your probe can't quite get the depth from that ledge. So let's pretend that this ledge is really small, like our probe can't even measure it. So what you would do is you need two features. You need a line scan and you need a cylinder. So we would create a line. So I can do define a line on the plane. And I'm going to go in this line, make sure the angles are 0, so it's perfectly straight. Normal angle, 90. That way it's not crooked. And the X location, we want it right on center here. Okay. Delete this. So once you have the line, you actually do want this line to scan beyond the step. So it's riding over it. So the depth or the length of the line. This is in inches. So we're going to go. You kind of want the same distance on both sides of the step. So let's say this line in reality is only a 1/4 inch long. So something like that. You also want your probe ball size to be as small as possible. That way you're getting as much detail in that step. Likewise, you'll go and set your point spacing to be really tight, like maybe 2/10, and your speed really slow. Because you want to just go over that kind of like a profilometer would. So now you have your line. Also, don't turn on the outlier elimination. You might just have the filter on. So in there, you have your line, but you also need the cylinder, which defines the axis direction. And then you choose, do you want the step to be this way or this way? So is the step near the larger diameter or the smaller diameter? Now your result, the little X here, is not going to be indicative of the real data just because we don't have any real data at this point. But then your step angle, sometimes the step has a bevel, so we could put 45. Otherwise, in this case, it's just 90. And then you're going to go and measure it. And in the simulation, it always fails to give an actual data because it's just a perfect straight line. but in the real scan, it'll have a little bump. And it's going to approximate where that step is. Not super accurate, but it's good if you don't have any other choice. Then lastly, the kink point. This one I haven't used hardly ever, maybe once. But the way this works is you're basically creating a kink from two nominal features, so like a line and a circle instead. And I don't claim to know everything about Calypso, so oftentimes I'll go and check out what's going on in here. F1 is your help. And here it's saying the tolerance feature is the feature we want to check. It says that we're going to use a 2D curve, which would be suitable, or you can use a 2D line or a circle. The nominal feature 1 and 2. So the first feature might be a line or a circle. So effectively, we're taking a line and a circle that has very little arc length and intersecting them together. But like I said, majority of the time, I've been using step point. Use a probe that is small as possible too. But if you do have access to other tools like a vision system or a comparator, oftentimes those will be more repeatable. So I hope that satisfies your curiosity on that. We're out of time already. It's been another fast, interesting session. Let's see, does anybody have any other questions? Let me see here. I'll go back to my screen here. All right, well, we're gonna call it a day. I'll plan on doing this again next week on Wednesday. Thanks again for joining and have a great day.